Hello, and Koji, thank you for that introduction. And Reinhard, thank you for the opportunity. It's a pleasure to be here. How's everybody? So we're going to move from very large scale to something that we can actually see more millimeter size things. But for those of you who were this morning at the industry session, you'll hear some of the same topics about how can we use techniques that are effectively DirectWrite in a sense to fabricate functional devices. I want to also acknowledge all my collaborators. The work that I'm presenting here today is their work. They are really the people that have made this possible. And this work is being sponsored by ONR. So let me get started. What I'd like to talk to you for the next 35 minutes or so is how we can use a DirectWrite technique that is laser-based. After all, we're here in Photonics West, so we're going to talk about laser applications. And so I'm going to go and explain through my presentation a bit more about this process that is known in the literature as laser-induced forward transfer. And in this cartoon here, not drawn to scale, show the basic components, and I'll show you more of those. But for those of you who are not familiar with lift, all what you need is a pulse laser, and you need a source of material that absorbs that laser. And once you have that, you can actually, with each pulse, you can transfer material onto a receiving substrate. So if you're familiar with inkjet, a lot of the things that I'm going to show you today are going to be very similar to that. We work with fluids. The original lift process was actually developed in the late 80s, and it was developed with solid metal films. The idea was to do repair of photolithography masks. And the principle there was the film, the donor film, will be actually evaporated metal, for example, chrome or gold, and the laser will actually melt and vaporize the metal. More recently, what we have discovered is that we can use the same principle, but to transfer complex fluids. And when we do work with fluids, the advantage is that we don't have to heat them up to the point that they melt. Well, of course, they vaporize. So we avoid that, which is better because we can actually transfer materials that will be sensitive to a change in phase, for example. So what I'd like to show you is how we can use this application, this technique, to print interconnects and print devices. And here's an example of some of the things I'm going to show you today. With the idea is that we want to produce hybrid electronics. Now, the word hybrid here, what it means is that what we want to do is take the best of both worlds. The idea of printing electronics is not new, and there's been huge efforts, very successful, using, for example, organic materials organic semiconductors to print things like displays, transistors for displays. But there, what you're trying to do is trying to build a transistor from scratch. The approach to using in hybrid electronics is, let's use CMOS or other already fabricated circuits, integrate them into a substrate, interconnect them, and now we can have effectively a part that is functional. And so I show here an LED, in this case it's a bare die, and I'll be using that terminology in the next, during my talk, and that is a chip that is not packaged. And you can see here the entire LED glowing. You see the scale here. This is about 1/4 of a millimeter. So these are very small devices. But these are the devices that you see, for example, in your phone or your computer that light up. And you see the connections that we have printed. Both the LED and the interconnects were transferred with this laser-forward transfer process or laser DirectWrite. So the goal is very simple. Can we actually go from a design to a printed part, but it's not a printed part that is faithful in the structural sense, but is faithful in the functional sense. So we have a design for a circuit, can we print it, and does that circuit then work? And so what we need to do that is we need to have a substrate, we need to wire up, we need to place the devices, and to connect between the wiring and the devices, we're going to need what I call these interconnects. So this can be done in steps, and if you do it right, you can actually end with a functional circuit. Now, the Navy is very interested in additive technologies, and these techniques, these DirectWrite techniques that I'm presenting today, these laser-based DirectWrite techniques, are also a subset of additive manufacturing. And one of the things that obviously is of interest for the Navy is, for example, the additive techniques will actually help on the supply chain. That's a huge problem when you deploy and you send a ship overseas, something breaks down, now you have to send it from the US, for example, to Japan, if it's based there. And if you could actually do that in situ, meaning that if you had a additive manufacturing facility, that will then allow you to, instead of sending the part, all what you need to do is send the data to make that part. There's other applications also that the Navy vision for additive manufacturing envisions, energetics, to do also for medical care, for sustaining of the expeditionary forces. But one area that we see ourselves fitting very well is on-demand systems. And by that, I just highlighted there the point that implies the ability to do embedded systems with sensors and electronics that can be set up for a specific mission on theater. So this is where we see ourselves playing. And if you want to learn more about this vision for additive manufacture, the program manager from the Office of Naval Research will be giving a presentation, Dr. Jennifer Walk, tomorrow afternoon on the 3D, the laser 3D manufacturing. And I encourage you to attend to learn more about what the Navy is trying to do. So under the umbrella of printing electronics, embedded electronics, that's what we have been exploring. And what we're doing is not unique. We heard also this morning at the forum on industry applications about this manufacturing innovation institutes that have opened up in the past few years. The most familiar one to everybody is America Makes. It's the institute set up to do 3D additive manufacturing, but there is a new one that some of you may not be familiar with that is called NextFlex. This institute just opened up about a year ago. It's located on the West Coast, actually in Silicon Valley. It's funded by DoD, and these are what is called, these are public-private partnerships. The idea here is to bring in both industry, academia, industry and academia, and plus the government to develop some of these advanced manufacturing techniques. And this particular one focuses on printing hybrid electronics. So again, we find ourselves that we're working in an area that is actually attracting a lot of attention. And the mission here for NextFlex is to develop different techniques, not just laser-based techniques, roll-to-roll techniques, imprinting techniques, and with an emphasis on DoD applications. And here I list a few of the ones, and I encourage you to go, I don't know if you can see the website for NextFlex, but if you just go on the web and type NextFlex, you'll get to that site. They are actually in the process, requesting white papers and proposals, and looking for both from academia and from industry. So under that umbrella, we've been working at NRL on these ideas of putting down electronics for quite a few years now. And I went back into one of my archive drives to try to get the old logo. This was the logo used for a program that is started by DARPA back in the 2000s. And because it's DARPA, they always like to have a nice acronym. So they came up with the term MICE, for Mesoscopic Integrated Conformal Electronics. And this was a very interesting program because back then there were some ideas on 3D printing. Stereolithography was available, also powder bed systems, but nobody had thought about doing printing for electronics applications. What DARPA wanted to develop with this program was the ability to print an entire circuit. Originally, the goal was to print a GPS receiver, and so under that program, there were several teams working, and we were one of them. And back then, what we showed is that we could use the lift technique, the laser-induced forward transfer, to print different types of devices, as I show here, that contain different types of materials. So some of this work is very primitive, very early on, but it showed the potential of a laser technique to do both additive and subtractive. So there's other techniques also that do this, they can do this very well, and I list a couple here, and there's a reason why I'm showing micropen and inkjet, is because these techniques share the property that they use materials that are in a fluid form. So they're printing either low viscosity inks as an inkjet or high viscosity paste like in micropen. And these techniques are well established, and they're actually in use by different groups and also in companies to do electronics. For example, inkjetting has been used to print electrodes for photovoltaics, for large-scale photovoltaics, solar cells. But the key here is that both of these techniques, you have to be careful about the material that you put on the nozzle or on the dispensing head, because you can actually clog that, you can actually block it, and you also have to worry about the nature of that fluid, if it's the right viscosity for inkjetting or for micropen. When we use the LaserForward Transfer technique, the laser DirectWrite technique that I referred to, the nature of the material is not that critical. We can actually make a paste of anything we want to, or a fluid of anything that we can mix. And sometimes we feel like we're painting, so we just take powders and we mix it on a fluid, and then we try to make something that looks uniform, and we spread it on a donor substrate, and we transfer with a laser. And this mechanism here, I'm going to go into more detail, which shows the nature of how the ejection, there's a jet that gets formed for low viscosity inks, and that leads to a drop. And that droplet then is what we collect and form then. As we repeat it, we form patterns. So we call this droplet here is our voxel of material. That's our single unit of printing, and we actually can vary that. So through the years, what we have shown is that with the laser DirectWrite, we can do both addition of material, additive material, but also remove material. And that is what, in my opinion, gives these techniques, these laser-based techniques, an edge. Because you have now the same tool, the same setup, and lets you do two things that actually complement, and I like to think of it as writing and erasing. So you make a mistake, for example, you can come back and you can trim your pattern. You need to drill a via, so you need to connect between two levels. You can do that with the laser. You need to make a pocket to put a device to make the hybrid electronic. You can do that as well. Once you have that laser in place, all what you need to do is adjust the intensity of the beam, intensity of your pulse, and now you can actually go from a very gentle transfer, where you're not doing any heating or you're not compromising the nature of the material, to ablation, where you can actually do micromachining. So here's an example of one of our workstations. And one of the things that you'll notice is that they're open. And the reason for that is that we work with different types of parts. We get end users that come to us and say, we would like to print an antenna, for example, on this curved surface. And so because of that, we had to design a system where the optics are above and the translation stages that let us now register and locate different points on a surface or on a 3D part independent. So they are decoupled. The other important thing is that we have effectively what we call our writing station. So here in this picture, you see a galvo head. So we can send the beam through a galvo scan mirrors, and then we can scan to write at higher speeds. Or we can send it through an objective set of lenses, so we can get higher resolution. But we can mount other things on this platform that then lets us work at different heights. So we can now then control the gap between our surface that we're working on and as we print. And in this picture, you don't see the laser, but we use solid-state, diode pump solid-state lasers. We usually work at 355 nanometers, and we work with repetition rates that range between a kilohertz to 10 kilohertz or so. We can go faster rates, but most of our work is done for prototyping and for research purposes, so that's sufficient. So here's some examples of what we have printed through the years, and notice, I'd like to draw your attention is the range on particle sizes. So we can print suspensions that contain nanoparticles of material. And I say material because I want to show you that during this presentation is that this technique is compatible with a wide range of materials: metals, polymers, dielectrics. In this case, we're printing here nanoparticles of titanium dioxide for making what is called an a Grätzel cell, or an electrochemical photocell, photodiode. But we can also print large particle sizes, which means that we don't have to have anything that has to be prepared especially for the process. If we wanted to inkjet this, for example, that would be very difficult. And in this case, these are actually both the anode, the carbon, and the lithium cobalt oxide cathode to make a stack structure for making a lithium ion battery. So these are the kinds of things that we can print. And also polymers, this is a loaded polymer loaded with carbon. Effectively, it's a chemiresistor as in the presence of a vapor, of an organic vapor, it swells and the resistance changes. So here is a cartoon, and this is not drawn to scale, but this is an easy way to visualize what happens when we fire a laser pulse. Laser is coming from above, and we have here an example of two types of fluids that we can have on our donor surface. So the donor surface could just be a piece of glass, and we coat it now with the material that we want to transfer. This is usually a few microns in thickness, and you can see that with the low viscosity, we form a drop. We form first a jet. That's the jet is originated from the collapse of the bubble that forms when the laser heats up some of the solvent and vaporizes the solvent, and this collapsing bubble leads to a jet that then forms a droplet. But we have another regime where if we have now a high viscosity paste, and just to give you an idea what we're talking about high viscosity, think about peanut butter. So we have materials that actually are designed, we use pastes that are designed for the screen printing, for example. And now, instead of having a bubble, we actually have more of a lamination of the material. Now, keep in mind that the material here is still a paste. The laser has not dried that paste. The laser hasn't heated up at all. It's just enough to shear the material away, and now we have a different type of transfer. So these are complementary because, as I said, this is not drawn to scale. The gap on which sometimes we need to transfer the high viscosity is going to be less. There's usually a gap between the receiving and the donor, and that's of the order between 25 microns and 50 microns or so. But keep this in mind because you're going to see examples of what we can do, especially with a high viscosity transfer. So again, here is just a representation, but here is now checking actually what the transfers look like. So we took two silver nano suspensions and transferred them on a silicon substrate. And what I want you to pay attention to is the apertures here. This is actually the laser intensity profile of the beam that is actually interacting with the donor's ink. And here you see we have a circular aperture, and here we have a square aperture. The intensities are pretty uniform. We blow up the beam so we get a relative uniform distribution. And in this case, it's the same laser, the same conditions. The energy may be slightly different, but we're talking about a small percentage change. Notice that when we transfer the low viscosity ink, the shape of the aperture doesn't play a role. We effectively get a disk on the transfer because remember, we created a droplet. So the way I like to think about this is we lost information. There was information on the pattern, on the distribution, on the spatial profile distribution of the laser, and when we work with low viscosity inks, we're not able to maintain that. And that's what happens with inkjetting, for example. So that's why the shape of the shape of the nozzle really doesn't play a role. But when we go to high viscosity, now what we have is what we call a congruent transfer. In those cases, the shape of the laser pulse is actually maintained and reproduced on the transfer. And this becomes very interesting because we're talking about a way now to transfer a voxel. So that's our three-dimensional printing unit, but that voxel can be shaped. We can actually adjust that. So here is if we look at AFM and SEMs of, again, these are silver nano suspensions of varying viscosity. So this is of the order of about 10 centipoise. This is of the order of a few 100,000 centipoise, and this is over 1 million centipoise. And you can see that we have a drop here, so that's why we end with a hemispherical shape. On the other hand here, when we have the right viscosity, we end with almost what it looks like a thin film. And there is no masks, no patterning, no material removed, and we can get very precise patterns. Of course, if we increase we remove too much solvent of that suspension, then our transfer falls apart, breaks while it's released. And if you want to be able to see that in action, a few years back, we actually borrowed a high-speed camera. These are the cameras that you see photographing explosions where you get many, many frames per second. In this case, we were operating at 100,000 frames per second. And so we then took our donor substrate, we took the laser and pulsed it, and we removed the receiving substrate so we could actually see what happens with the ejected material. These 3 videos here are all done at the same frames per second, so the speed by which material transfers is going to be, that's the actual speed, in the sense that if you see something moving very fast, it's actually moving at a faster rate than something moving slow. And the scale here is 1 millimeter to give you an idea of the size. So if I play these videos, what you're going to notice is first the illumination from the laser pulse. The laser pulse is hitting right at this point here. This is the interface between the donor substrate and the ink. And you notice that we have actually 3 different regimes. And you can see that the dry transfer is completed while what we call a decal transfer, or this congruent transfer that I mentioned before, is still going on. And the videos are repeating so you can see it again. And here is the jet formation and a drop, just being ejected. So what we see, what we imagine that is happening, these videos confirm, and these videos are available on the web. Sorry about that. Let's try to get them started again. There we go. And just to give you a scale, the speed here at which this foil, and I say foil because we think of it, but it's actually not a solid, it's still a paste. So think about like a cookie cutter that you are breaking up. This is about 300 microns, a third of a millimeter. They're the same size on the 3 cases. And this is moving at about a meter per second. That's how fast it's flying. Now you notice how it flaps and it moves because actually it's flexible. And this is being done in air. So there is actually a drag involved in it. So this is a very interesting regime that lets us now transfer entire foils, if you will, with a predetermined shape. We just have to change the aperture. Now we can vary that. So here's examples of things that we have transferred using this congruent mode. And so we can change the aperture to do that. We can also transfer larger to and smaller. This is of the order of a few microns. Notice the change in thickness too. As we make larger and larger transfers, we also have to increase the thickness. If not, effectively we rip that foil apart. The other interesting thing is that we can change the coating on the donor substrate, and we can make it thicker or thinner depending on what we're trying to do. These are 3 examples. Each one of them is 1 single laser pulse, and you can see that we have certain range of thicknesses that we can print. The scale that we can get to about the resolution is of a few microns. We cannot go below that because now what happens is think about the perimeter and the surface of these voxels. We're trying to shear this part from the ink, from the paste, and at some point, the perimeter, that shear energy is so high that we actually end with we end damaging the voxel and the transit. In other words, we have to increase the energy to a point where we rip it apart. But because they're paste, when we print them, they actually, you can see here, I don't know if you can see the little details, that is an individual voxels that were printed next to each other so we can make a continuous line that way. And that's how we make now the electrical connections. We can also stack these things together, and we can also make freestanding structures. Again, you notice how it was being released, and if we do that right, we can actually capture it and make bridges and also cantilevers. So to put this in perspective, another thing that we have looked at is what is the range on the size of these voxels that we can print. And this is an example showing here 5 micron by 5 micron square voxels to an entire, this is a pattern that is of the order of a millimeter in 1 dimension. And that each one of these, the individual voxels here and this entire pattern, were generated with 1 single laser pulse. So as long as we have enough energy in our laser source that we can expand the beam and then create a pattern here, we can actually then print it. So one of the comments that is always made about these techniques is that they're serial in nature, and how fast can you actually print? And I want to thank Dr. Hennig here for letting me use this slide from a project that he worked on years back, where they actually designed a large throughput roll-to-roll printer process based on the LaserForward Transfer. And the approach that they use is they use, instead of using laser forward, they use laser back transfer, but it's still a transfer mediated process using lasers that, in this case, you had a continuous roll with the ink that will be coated. The laser will actually then, the ink will be semi-transparent to the laser, heat up the metal backing, and that will then create the bubble, and that will lead to the droplet being ejected. And so in close proximity, there will be the paper that will then be moving constantly. This laser will be scanning at a very high rate. And what is, in my opinion, impressive is that the speeds that they could achieve with this machine, and they actually built this. Each one of this is a printing unit. And if I remember correctly, these are for the 4 colors. The laser system is in between. There's one here and one here. With the polygon, they could actually split. So the duty cycle, they'd be able to use both sides. So the efficiency was extremely high. And with that, they could actually then demonstrate it. These are printing artistic or graphic inks. This were, in this example, is not an electronic ink. But you can see the size here of this sheet. This was a test run that took 18 seconds to print that way. And I like to show this example because even though we're using a pulse process to print voxels, those pulses could be going at a very high rate, in this case, in excess of 25 megahertz. The other interesting thing that we can do, and again, this is just to address the issue about are these processes scalable, is that speed is one way. Another way is to change dynamically the shape of the voxel that is being printed. And so I showed you before that the congruent transfer lets us do that. And if instead of using an aperture, which is what we have done in some of our systems, and if instead of that we put a digital micromirror device using, for example, one of the Texas Instruments DMDs, we can now dynamically change the shape of the laser beam that is going to impinge on the ink that we're trying to transfer. And dynamically means that I can change, every pulse can be a different one, as we show in this cartoon, in this example. And here's the actual product of that. This was done on silicon again. It's nice and flat, so we can actually then get good images. And you can see now that entire character, and this could have been a pattern for an electronic interconnect, can be printed in a single laser pulse. The interesting thing too is that we can do patterns that would be very difficult to do, or impossible for that matter to do with a mask, where we have here a grid. And if we were to try to do this by traditional printing techniques, say inkjet, we will get an overlap between the two members of the grid. And if we need for an application where this needs to be all uniform in thickness, it will be very difficult to do that. With the laser transfer process, that is not an issue. So this is an example of how we can actually increase throughput with these techniques. Finally, the last example of the capabilities with the laser transfer process applies to the idea of making a hybrid circuit. And in this case, what we want to do is not transfer an ink, but transfer an entire device. So we think of that as a brick. We want to actually just launch bricks across a gap of 25, 50 microns, and capture those bricks and now build a circuit that way. So that's actually done in industry. That's, you have machines that do that with all your semiconductor components and also with your passive devices like your surface mount devices. And these are called pick and place. You have a machine that grabs the device from a tape and puts it down on the circuit board, and then it goes through a reflow oven, and now you make your circuit. So playing on those words, we call ours lace and place, because now instead of a mechanical actuator, we're using a laser pulse. And because the devices are larger, we actually were working using an excimer. That gives us a larger uniform beam over areas that could be over a millimeter square. And instead of having an ink, now what we have is a donor substrate, a transparent plate, with devices that are attached using a polymer layer. The polymer works beautifully because it absorbs the laser, vaporizes, and that vapor pushes the device forward. And in the process, we do not damage the device. I like to point out that we are transferring these devices with the pattern side facing up, facing the laser. In other techniques that they use long wave lasers to do transfer, using effectively a thermal process rather than a ablative process, they have to put the devices upside down because they have excessive heat that can damage now your semiconductor patterns. The disadvantage of that is that now your device is facing down and you don't know where the interconnects are, you don't know where the pads are, so it makes it more difficult now to make a circuit. By transferring the devices face up, it's relatively easy for us to come in and now connect them and make a circuit that way. So with lace and place, we actually have been able to make arrays of devices and with the goal of moving towards this hybrid approach. And here I show you another frame-by-frame image of, these are dummy devices. These are 1 millimeter square silicon chips that you can see once the laser is fired, and you see the chip flying away here. So there is the chip stock, the laser fires one pulse, and the device is flying away. And one important thing to note is that this is a pretty thick piece of silicon because we just took a regular wafer, but we have actually shown that we can transfer devices or substrates that are as thin as 10 microns. And that is very important to make flexible electronics. You can actually take a patterned wafer, you can thin it down to about 20 microns or so, to the point that you can actually wrap it around your finger, and that wafer is still functional. But now there is no technique, the mechanical pick and place actually breaks those wafers, that you can take that singulated dice, once you dice it out, to place it now on your board to be able to connect it. With lace and place, we can do that. And here on the left, it's an old video that we took when we were actually setting up the process that shows right now what you see here is a pocket. This is polyamide, it's a substrate that we're using. It ablates very well at 355, so we can make then a receiving pocket. And now this is what the operator is seeing on the monitor, and you can see right now that it's moving the donor substrate, and each one of these is a device that is being attached with a resist, with a polymer layer. And what's happening here is when the laser is fired, you notice how the device is no longer in focus because it just moved down and went into the pocket. Now this has been done by hand for this demonstration. In other words, we have two sets of stages. They are decoupled. So we have XY motion for the substrate underneath, and you see it moving right now. And we're trying to move the pocket to a predetermined spot. And we have now a stages to move the donor substrate. We call that the ribbon, like in a typewriter, so we can line it up. But this can be done all automated. It can be all done with machine image recognition. So this process can be done at a very high rate. And we've done calculations where this can actually exceed by over an order of magnitude the fastest pick and place, mechanical pick and place machines available. So this is how we put in the devices. And here's an example of some of the things that we can transfer. And this was done more than anything to do a proof of principle. In the part that I like here, I'd like to point your attention to the right side, is that these are very different components that we could transfer with a laser from an entire device. This is actually a timer circuit that is the bare die has not been damaged in the transfer steps. And the LEDs that you saw before on the video before, also unpackaged. But we can transfer beams of silicon or pieces made laser cut. This is a gear that was laser cut out of polyamide. So the process actually is very flexible. All what we need is a laser pulse that is about the size of the object or the brick that I referred to before that we want to transfer. So here's examples of what we can actually transfer. And again, the LEDs and the interconnects that we can print. And this is putting it all together, just embedding these devices now on a curved surface. These are LEDs, then placing the connections and the wiring. And so that's how we can move to hybrid electronics. So I think I'm out of time. Is that correct? 2 minutes. So again, we can show interconnects as well, and this is to put in, take advantage of the freestanding structures that we can make. But the last thing that I had here was, and I'm going to move through this, was to show that we can also transfer metal foils when we need a high current application, if we need several amps in a circuit. And one of the issues that we have to worry about is we want to shape the foil so it can accommodate thermal mismatch strains on the part. And we can do that also with the laser. So we can shape first and we can transfer later. And here are examples of some of these interconnects that are solid metal. This is no longer a paste that we use. We're actually using copper foil. And here's a circuit that we can actually demonstrate it making those interconnects. And the last thing is we can combine the laser transfer with additive, in this case, fuse deposition modeling. So we, in the Z station that we have, we can add now an extrusion head, and we can now design a part. We can fabricate it, put the devices. In this case, we did the interconnects by plating first and laser removing. But in this case, we use laser structuring, laser direct structuring, where the resin that we print actually has metal particles that you can expose with the laser, and then you can electroplate, and now you can add your circuits. So to finish, I want to leave you with some last thoughts. Is the advantages with the laser DirectWrite is that we have both additive and subtractive. We don't have to worry about nozzles. The material have huge flexibility and lets us put in devices. And so with LDW, what we can do is things like we can do the congruent transfer to print complex fluids. We combine it with a DLP, and we have dynamic adjustment on the voxel. Fabricate standing structures for interconnects. Put devices, entire devices for lace and place, and integrate with 3D printing. And with that, I thank you for your patience, and I'll leave you with this last slide of some examples, and I'll be happy to answer any questions. Thank you.